is the introduction session. So just a reminder, you can clone the repo or download a zip of the repo on GitHub. And so with this, it's for the workshop part or the exercises, and those will be live examples I will run through afterwards to be able to experience the joys of SF. Otherwise, today we'll be covering the introduction. We'll be speaking about why SF and why it's so loved in the spatial world. We'll look over the fundamentals, a bunch of functions that are useful, and we'll give you just the rundown so that you understand what it's like prior to doing real life examples, because those can get a little hairier, and talk about other considerations, and then we'll do the exercises. So as Jasmine said, we work at PlumeVue. We're a consultancy. We do digital transformation. And so my background, well, both of us have backgrounds in engineering. I'm a mining engineer and Johannes is an industrial engineer. And we both specialize, I guess, in data. We did our master's at UBC together several years ago. And since then, we've been working in advising our customers on data pipelines, data solutions generally from a wide range of domains. And yeah, where I was exposed to spatial analysis was using GPS coordinates and geostatistical models of ore deposits and inferring what rock type was being extracted with the machine guidance. And so it was mainly in the mining industry, but after that, Johannes has been using it a lot in environmental spaces. Maybe Johannes, you want to introduce yourself?
Yeah, that's a good introduction. Yeah, I would say environmental sciences is the main place where I've used SF, the SF package. In some bid projects, I've used it with like visualizing trail running data and things like that. So it's quite versatile. But yeah, Vera will be leading this workshop. I'm more just here for the technical support if required.
Yeah, so disclosure, I'm by no means an expert in spatial analysis. I just know enough how to break things, and Johannes is here if I panic. So he'll be able to fill in on the technical side as he has quite a bit more experience with SF than I do. So yeah, direct your questions to him. Thanks. So here's the introduction. So SF stands for simple features. One of the reasons SF is very useful is that it's implemented in ISO standard, which means that it's a standard that's been applied across the world. So the interoperability between other systems and R is great. By using SF, we're using the same standards. So with all the coordinate systems and whatnot, we're all on the same page. It doesn't make it that much easier, but at least it removes some of the confusion. It's the successor to the SB package. And so it's a very powerful tool, and yeah, it just standardized the way we encode spatial vectors. So I think also something to note, you'll maybe see this a lot in Stack Overflow or people asking questions. It's built on other packages that were built outside of R. So GDAL, Geos, Proj, and those are dependencies. So if you encounter some issues, just know that those are common names that come up, and it'll help you in your troubleshooting to identify or isolate the error if it's part of one of those. Also, don't want to sugarcoat it. Spatial analysis can be very difficult depending on the complexity and the sources of the data. It's not always clean, and it's not always done the same way. And so depending on how many data sources you're bringing in and whatnot, you may encounter more errors where in the end, it will just require you to dive deeper into the theory behind these, the tools that you're using so that you can best troubleshoot. But otherwise, we can do quite a bit of visualizations and analyses with just the basics, which is what I'll be showing today. So so simple features represent geographic features as objects. So you can have geometry, which is like the point, the polygons, the lines, or you can have attributes, which is similar to a data frame, a regular data frame. And so these are joined together. You have the geometry column, and then you have the attributes, the non-spatial data. So the examples here are the multi-point, which is so it can be locations, it can be landmarks on a map or not. Then we have line strings, which could represent, say, a road, the center line of a road. Multi-strings could be, say, the boundaries of a road, so a sidewalk, the outline of a road. Then polygons are contour shapes of areas. Multi-polygons could be a collection of them. And then geometry collections is a mixed bag of objects. And so when we look at these, we have to think that there's a lot of specialized, even engineering software or in other fields that are using this type of language, and they're using it to design very complex systems. And so you can imagine some of these can get quite heavy into the mapping. So SF classes, we have the main one, which is the simple features object. And so if you look here on the bottom from the docs, you'll see the last 3 lines of the code that's output are, do I have a pointer? Sorry. Maybe it'll be easier. Can I, yeah, sorry. Sorry, I don't use Zoom that much. Where would I find this pointer?
Let's see.
Or can you see my mouse?
I can see your mouse. I remember
Okay.
that there was, but I can't quite remember. Is it in your like share kind of like toolbar? Is there something?
No, it isn't, but it doesn't matter. I'll just use my mouse. That's fine. Oh wait, there's annotate. There we go. Okay. No, this might cause me issues, so I'm not going to annotate. Okay, so then the last 3 lines here at the bottom are like rows in a data frame, and then the simple feature is a row. Then we have a simple feature geometry, which would be within a column. Well, okay, the simple feature geometry list column would be the whole column. And then the simple feature geometry is the element within a row and within a column. So it would be all the coordinates that pertain to that element. So the beauty of SF is it integrates very nicely with other tools. And so the tidyverse that is loved by all, we can easily manipulate the data frames with all of the tidyverse dplyr functions, which allows us to do quite a bit of analyses, and then it maintains its elements or its geometry elements, and does a special handling for special functions. And then you can use geom_sf when you're plotting the SF objects. And this one will automatically handle the different geometry types. It'll handle the projections, the coordinate systems and whatnot. And it's easy to combine with all sorts of ggplot features like the visualization aesthetics. So here's the hairiest part, in my opinion, of spatial analysis, and those are coordinate reference systems. And so the way I'd explain it is the world isn't flat. It's not flat, it's a round sphere, as in an ellipsoid. And it has as well terrain within local environments. There's quite a bit of terrain, there's elevations, topography. So that being said, when you're measuring areas or distance, you have to understand in what plane you're measuring them. And to do so, you may use different projections, and they'll have different advantages and disadvantages. And so it's always a compromise on which standard you use to do these operations or these spatial operations. And so here's a sample of an S3 cheat sheet that shows you a bunch of the different properties and usage for each of the different projections. And so what you can do once you understand the different facets of it is you can go and find the best projection for your use case. Or you can Google and say, I'm trying to do this, which is the best projection that's used. And so it's good to note that these are not simply the parameters that you're looking at aren't reserved to the operations you're doing. So you're calculating a distance or the area, but it's also to where you're situated in the world. And so those are things to consider. This is an example of a bunch of the projections. And so you can just imagine how things get distorted depending on how the layout is. And so that's the main purpose of this slide, not to overwhelm you, but there is the right projection for you. It exists. And so CRS there's a function that allows you to read, sort of like figuring out what the type of your variable is. So you can do the same with figuring out what the coordinates are. And so in this case, you would do st_CRS, and it would give you a whole blob of code, and one part of it will show you what the code is. And this code here is an example of, this one is the latitude and longitude, the typically used one that we see in Google Maps and whatnot. And so what you can do is you can set the CRS by using this function, or you can transform the CRS. And so the difference being that if you transform the CRS, you will overwrite the geometry and convert it to that reference system. Meanwhile, the setting it will not overwrite the data. So here's a breakdown of a more complex example. There's quite a bit of flexibility. And so depending on the level of precision that you want, you'll want to tweak these. But sorry, mostly I'm showing you so that you're not overwhelmed if you encounter it in the wild. And so the proj is referring to the projection. So like that colorful slides ago is one of these. And in our case, when we're looking at Canada, often the Lambert conformal conic one projection for a large area, so the whole of Canada, which happens to be a very big country. Then we have the so the boundaries, the latitude, longitude, and this is like a sanity check to make sure we're in the right area, and the center point. So that 0 and long 0 will be the center point. And then we have the easting and the northing, which, correct me if I'm wrong, but I think it could be because the Earth is round, at some point, the sheet of paper, the ends will meet, and you don't want to have part of your map on the other end of your sheet if you're trying to filter for a section. So I think this is how you adjust it. So say you're in the Polynesian Islands, you're doing the coast of America and the Polynesian Islands, you don't want to have them at two opposite ends of the map because that's the convention. You'd want to bring them together. And then datum. So these are ways or conventions of measuring the Earth. And then units would be meters, kilometers, for example, and then no def. I guess it's not apply default values for certain parameters. Okay, so now we get into the fundamentals. I'm going to go through them relatively quickly. The idea is that we want to get a visual with simple examples of what the different functions do, so that when we do a live example and we start playing with real maps, you understand the mathematics or the operation that's being done behind these functions. But they're simple and so they're quite intuitive. So reading and writing, similar to with the CSV and whatnot, quite flexible. You can use all sorts of formats. So shapefiles is one of the most common ones. If you want to find information to do some sort of analysis, A lot of it is available online, open source, and so you can use government websites. A lot of them will offer portals that allow you to download these, and then otherwise, other studies that people have done, there's a whole variety of them available. Things to consider would be the precision of it. So you'll see sometimes the boundaries have more precision or not. So that's always something to take into account. How precise do you need the objects to be? And mind you, the size of those objects will be quite big if you want a high precision of, say, all of Canada. So something to consider. And then you can also write them to share them with people that are using other software or language. Then there's spatial operations. And so these ones can be geometric operations like buffer and centroid. There's topological relations, so intersects and ST within. We can do spatial joins of these ST objects or SF objects, and then aggregations. So here's an example of creating an object. ST polygon allows us to take coordinates and create a polygon. Then the code that isn't highlighted is code that isn't using the SF library. And so what we're doing here is a translation. We're manipulating B0 to create other variants without having to create new polygons. So we're moving it aside, and yeah, we're moving the shapes around and saving them as their own variables. And then what we do here at X is we're creating our a simple feature, and it's just a combination of the three. So as you can imagine, this would create a like a data frame with all of these. Then we do the same, this time manipulating it differently and saving it under A. And this one, we create another object with this time having four, it composed of four of them. Then we plot them, and we see the B shapes are red and the green shapes are the A variables. So this will be important because we'll be doing operations. So memorize this shape, but I'll show it again. So here are some operations that return geometries. We have ST union. So this one is combining the shapes. So the one on the left is the original, and the one on the right is when it's been union. It kind of seems like one part is separate because of that one, it connects at one point, but is actually just one shape now. Then ST buffer is interesting because we can have it where it is creating a margin on the outside, it's expanding it. And then we can also have it where it creates one on the inside, like here. The black line is when we do -2, it goes on the inside, or -0.2. And you can do both if you want to create a fat line. Then ST boundary. So this one is extracting the perimeter of a spatial object. And so not to be confused with BB-box, which is extracting the bounding coordinates. So the min and max on every side. Then we have ST convex hull. So this one is creating an outline to the shape. And so in this case, we were using X as is, and X was 3 different box or squares. Meanwhile, doing it to U was the one that had been unioned. And so it was one big shape. So that's why it behaves differently, but it's taking the outer edge of the original points. ST centroid is giving the center point, and so it's a mathematical equation for finding the center point. And this one, since it's been unioned, is also being applied to all 3 of them. And ST intersection, which is one of my favorites because you can do quite a bit with that. If you don't have the map of exactly the area that you want, you can create it. And there's all sorts of different things you can do with this. So ST intersection, we've created a union with the elements. So the X are put together and the Y's are put together. And then we say what territory is shared by both of them. ST difference is also allowing us to do somewhat the opposite. So this first one is the shapes as they are. And then if we do the difference of X and Y, we're prioritizing X's area and we're deducting anything that Y touches. Then we have difference of Y and X, which is doing the opposite, is prioritizing Y's area and deducting all of X. And then we have the sim difference, which this one is doing almost like an outer join. It's taking everything that isn't overlapping from both X and Y. So here's an example of how you can use intersection to create your own submap. So here I downloaded a shapefile for North American rivers, and I had BC, a map of, or an outline for BC, and I wanted to see the rivers on BC. And so I did the intersection of both. I got rid of all that noise and just created the BC one. Okay, other considerations. SF is generally faster than ST. Pardon me for the capitals. And then some operations can be slow if you have very large data sets. So always use the level of precision that you need, because more is not more. And then if you need to simplify, so say you don't have a choice, you can use ST simplify, which will make your file smaller. And if you have really large data sets for the attribute side, you can use data table, but I really strongly, I don't think you'll be able to do SF operations on it. So you'll have to convert it back to an SF object after you've done all your manipulations. Okay, let's play. And so I will upload this to GitHub as well, and you'll have some resources. I highly recommend the SF articles. It really goes through everything in detail. Maybe a bit too much detail sometimes, but there's 7 of them, so you can stay at the lower levels. And then spatial analysis workshop. This was a course offered by someone in 2020 that was it's a good rundown, and there's good videos. There's a lot of videos online, so if you want to deep dive it, there's a lot of options. And then the Quarto theme that was used was by Beatrice Mills. Okay, so let's move into the workshop. Any questions so far?
I don't see any in the chat right now, but feel free to throw anything that you think of as we go.
Okay, so we'll dive in. So today, for the visualizations, we're going to stick to Canada, and just a moment. Can everyone see an empty R screen?
Yep.
So what the way I'm going to do this is I'm going to be copy pasting code from the file that was shared on the GitHub repo, the one called workshop_SF. And this will allow us to go through it bit by bit. And feel free to stop, ask questions in the chat, or interject if something is unclear. We won't be doing live coding because there's a lot of visualizations and it'll take too much time. But if I'm going too fast with anything, any question, just interject and I will do my best to explain it. So first off, the shape files. Well, no, we'll do the libraries first. Yeah, so if you want to follow along, you can do it by copy pasting or running the code from the workshop file. And so as far as libraries go, we tried to keep it minimum, but SF obviously dplyr and ggplot and the tidyverse. And then this LWGeom was used for calculations such as area, and then the units is used to change the units. I don't think I'm actually using it, but just in case, it's a useful package to do with SF. So then another particularity, and so there's some particularities in here. Obviously, we could have made the world perfect and make it look like everything is easy and glossy all the time, but it isn't. So here's an issue pertaining to this part of the code. and it made it work afterwards. So if you want to know more about the spherical geometries, you can check out this GitHub link. So our first step will be to load the shapefiles. When you're loading a shapefile, you're going to have often a zip folder that contains a bunch of files. So you maintain those files, but the one that you'll be looking for usually is the .shp file. And in this case, I got the world map, the Canadian provinces, the Canadian districts, so the voting districts, and then a Vancouver specific one for schools in Vancouver. We're going to go down the educational route today. And so first off, I want to explain a bit how I should run it. I should run this. I'm going to show you some examples of projections that give you a better understanding of how the world can get distorted based on the different projections. And so if we just, as we take a shapefile, usually they do come with their own CRS. And so in this case, it's the EPSG 4326, which is a latitude longitude one. And so we can just plot it as is. So here's the world map with this projection. I think we've all seen a map that looks like this before. Now, in the next step, I'm going to remove Antarctica because it messes with some of the projections and takes up the whole map, which is not ideal. So in this case, they use an ISO standard in this data set, so we can remove the one that says ETA, which is Antarctica. Now we have a world map. And so for those that are unfamiliar, the data frame will just look like data frame, a table with all this information that pertains to each of the countries. And so ggplot will recognize its coordinates and we'll plot. So I'll run all three of them. So these are the different projections. We have Robinson projection. We have the Mercator projection, which looks nice and spacious. And we have the Mulholland projection, which looks a little warped. And so they each have their advantages. The Robinson projection is a compromise projection that reduces the distortion of all the map properties. The Mercator projection preserves the angles, but it significantly distorts the area. And we've all heard of this one, the controversy of it making Northern Hemisphere look a lot larger than the Southern Hemisphere. And then the Mulholland one is the projection that preserves area but distorts the shape. So this is important to note because if you're trying to measure the area, you'll want to choose a projection that maintains area. Meanwhile, if you're trying to draw on maps and routes to things, you may want to favor one that keeps the distances. So then the next step is we're going to zoom in to Canada. So here we just filter for Canada. Then we plot Canada, and in its original projection, which looks like this. So as you can see, you can note certain details. Like here we have the straight line on the bottom, which makes it look like a grid. The latitude longitude just looks like a typical square grid. And then here is the Lambert conformal conic projection. So this one is favored usually for Canada because it's a good balance of area and shape for this region. You can imagine for a country like Canada, it can be more difficult because of its size to strike that balance. And so if we want to use that function where we figure out what is the the CRS for each of these. Take a look. And so this is the raw line. It's a little more complex for the Canadian provinces, the projection string. But then with Greater Vancouver schools, it's the NAD 83, which I'm pretty sure is the longitude latitude one. And same thing here for, oh, so there's no units. Is that right? Oh no, sorry, it's this one. So here, this is using meters, and then I thought this one also used meters. Am I mistaken? No, no units. And so that's not a big deal. So for this one, oh no, that makes sense. Okay. So for the CRS here, because the CRS is, there's a lot of them and you can play around with it and you have different operations, you may use it for different things. So you could actually name a bunch of variables for the different types of operations that you're trying to do. And that way you could just call upon those variables. And if you decide one is better suited, say you're working in one area, you could switch it and not have to change all of your code bit by bit. So that's a good practice to do. In our case, we're using Albers because it's one that's favored for British Columbia specifically. There may be a better one that's suited for Vancouver area, but we'll work with this one for now. And then what we want to do is make sure that all the different SF objects will be matching in their CRS. So we're using ST transform. So we're really overriding those columns into the right projection. And so, and then we visualize the new projection. And this is the new Canada, which is puts BC nice front and center. And so we want to make sure, again, validate that they are the same CRS. So we see that it's true when you run the equal. Okay, so now we're going to zoom into British Columbia.
Veronique, what happens if you try to plot something like with two different projections? Like if you didn't go and do the ST transform beforehand, you forgot that step, and you just went ahead and plotted your data.
So it'll depend on the operation you're doing. In certain circumstances, and Johannes, correct me if I'm wrong, but I'm pretty sure ggplot will understand and convert itself. But other operations, you will get an error and it'll tell you that the SCCRS does not match between X and Y, and then you'll have to go fix that. And then you have to decide which one do you take. So it helps to understand what you're trying to do to decide which one you keep and which one you move past. But it really depends. Also, are you trying to output this and give it to someone to look at a map where they understand it nicely? Because often longitude and latitude is the right one for that. But any other operations, you may want to focus on a specific CRS that's for that area. So for example, I worked in a mine in northern Quebec, and we had local coordinate system. And so I had to convert that local coordinate system into the local S3 code or EPSG. And so, yeah, and then you do that. You're doing it a lot, depending on what you're trying to accomplish. You're converting often. So ST_transform is your best friend. It's probably more important than intersection. But yeah, I rambled a bit, but did that answer the question?
Yes, completely. Thank you.
Okay.
And I don't think anyone will forget to converge their projections after this.
I would tell you try it. If it works, yay. And if it doesn't look funny, if it doesn't work, then you know why. And it will tell you. But yeah, it's a good point. At the end, we do an example with leaflet and we get to validate with a map that the boundaries are looking good, and it's definitely sanity checks are important. So this is, sorry. Here we're doing the British Columbia specifically, so we're again filtering the Canadian provinces to extract the one that has the name British Columbia. So often with government documents, you'll have French and document shape files, you'll have English and French. And so often you'll just have E or F showing up in variable names. And so that's just a little hint there. And yeah, so this is the British Columbia, the first one. So just plotting it as is without doing anything to it. And then this is Canada with all of its electoral districts. So something to note as well when we're talking about precision is you see here we're missing all of the waterways, the lakes, the oceans, the sea. The same here when we zoom into BC, you'll notice that. And so it's just something to take into account. What are you trying to do? You may want one that has these inherently, or you may have to create it yourself with other shape files. I'm pretty sure we do this, an example of this. So yes, and then the next one is just extracting BC. So this is an example of how you would do that. You do the intersection of both. So you're taking this massive map and then you're saying, okay, what's the commonality, the common territory? And we get this with the districts. Okay, so then now we get into the schools. So we store this data frame. Maybe I should show you the data frames to give you an idea of what it looks like. So this school data frame will have the source, a lot of attributes, the name of the school, and then address, locality, here are the coordinates, a lot of the district name.
You downloaded, did you download it from kind of open data?
Yeah, the open data portal or the BC one, which I will put links to where each of these data sets come from. But this one, it's a BC government website. A lot of the more district ones and whatnot, those were all from StatsCan. So here's the geometry column. But you can also access them in the GitHub repo. Okay, so that is, so yeah, we have the BC districts and we have the Greater Vancouver schools. And so we plot them and it's all the way down here, a little frustrating because you can't see anything. So we will remedy that. Now, there's probably a lot of ways of doing this, but the SF way would be to create the boundary around these locations. And so what we're doing here is adding a 5-kilometer buffer to make sure, well, okay, the first one is just using the STB box function. And so this one gives you a min and a max for Y and X. And so that's really the extremes of the territory that's covered by all the red dots. And then we're going to want to turn that into, because it's only coordinates right now, we want to turn it into an SF object so that we can use it as a visual aid when we're doing, well, we can use it as a boundary within other operations. So this next step here is visualizing. So as we said here, the boundaries, we're using them as the base of our plot, and then we're looking at the schools. So overlaying. So this is what's nice as well about GeoMSF is that we can just overlay them and use different SF objects and just layer them on just as you would with ggplot under other circumstances. And so in this case, the little frustration I have is that we have dots showing up on the edges of the map, and that can be misleading. So what we're going to do here is create a buffer around it. So this buffer, so depending what, so that's why looking at the units is important, because here we're in meters, so we have to do 5,000 meters rather than just 5 kilometers. And so, but the equivalent of 5 kilometers effectively. And so we create this buffer, and then we plot it again, and we can see the outline of due to the buffer. So this is one way of doing it. Now, if you're very picky and you don't want to have the outline rounded like that because of the buffer function, you can also use convex hull, that we saw earlier. So convex hull will, oops, create R1 shape, R1 geometry set, and then plot it, and we see the outline. So this is another representation of what convex hull does. It really takes the outside and draws straight lines across it. And then if we want to use buffer again, we get this beautiful map. And so this time we've applied a buffer, again, 5 kilometers, and we plotted it. And had to turn it again because we used VBox. We had to plot it. So it's a bit of a roundabout way, but at least we get rid of the outline, the circular outline. And every time you use VBox, because it's returning 4 coordinates, you need to, or at least in 2D 4 coordinates, you need to transform it back into an SF object. Okay, so now we have a map, but this doesn't tell us much. We don't even know where we are. So the next step will be to apply the districts to this map. So we have the Vancouver districts, and this time, again, if you just were to plot the Vancouver districts, it would be, the BC districts, it would be much bigger and frustrating. So we want to apply the boundary that we found from the schools and apply it to the BC districts SF. So we do the intersection again, and then we plot it, and we get a localized version of the map. Now we get into some deep IR analysis. We get to crunch some numbers. Now we don't have a ton of numbers in this educational data set, but there are a lot of different resources, and the world is your oyster. You can join these tables together. And so when you're joining the different various sources, you may have like an example here, the Greater Vancouver schools, which are specific schools. And so you may not always have the same level of granularity. So if I say I got one that had all the different scores, but this one was the averages of all the students, but it was pertaining to a specific area. And so I believe it was a district, but see, like, is it an education district or an electoral district? It's all things you need to validate. And so in this case, I don't know that much about schools and their scores. So I'm going to, but we're just going to stick to the schools and count them. But just know that you can join these data frames together, so you can apply the attributes from another data set to your SF object and maintain the geometry so that you can plot them and do other operations to them. So here, the schools per district, we're looking at the Greater Van schools, and then we're joining with the Vancouver district. So if we look at this again, just so that you follow, it's just the name of the district and its geometry. So the one we've been plotting over and over again. And then the Greater Van schools, again, is the schools and all the information relating to the schools in an area. And so what we're doing here is we're joining both, and we get we have here the added information to the schools. So let's just do a sanity check. What was Greater Van School? Okay. Much just that, right? So that's what happened is we applied, because we're joining this way, we applied the information from the Vancouver districts to the Greater Van schools. Oh, we did it there. Okay. So everything looks good. Then we use the PyR to do a summarize. So we're counting the number of schools per district. And so here we just get the summary table of the count per district. Then we're joining again with the Vancouver districts. We're joining the number of schools per district by Fed name, and then we're plotting. So this is an example where we used dpyr's left join here, and then we used SF's join up here. And so there's different situations where you would use each, but if you're only merging the attributes, you're safe to use the left join. And we're not trying to apply a geometry to the Vancouver districts. Okay. And there's beautiful plot. So again, this is looking better in the sense that we get an idea, but I don't know about you guys. I have no idea where I am right now. All I know is that this little area here seems to have the most schools. So we move on, try to make that a little bit better. So what you can also do is you can create a tibble or a data frame with coordinates and then create your own SF objects with the hand collected coordinates. So say you're choosing spots, it's very easy. You go on Google Maps and you right click on a point and it'll show you the coordinates and you can copy it by clicking on it. And so then you paste them and create your own little data frames. So I've created this one to be able to plot it on top of our graph. Because we don't have the waterways, it's hard to orient ourselves. So this will be a lot easier. And I didn't want to clutter it with all of the different labels of the districts. So this is what we get. So for this one, we're using, again, the geom of the Vancouver districts, the geom of the major cities that we just created and transformed into the right coordinate system. Then we have, again, just the school count was already joined to the Vancouver districts, so everything we need is there. And the labels are determined with the geom SF label function, which you can add a nudge to move it. And so this one's important to know, am I working in kilometers? Am I working in meters? It will affect the nudge number. So this is what it looks like. And so we can see that it's probably Port Moody that has a lot of schools. Okay, so now we want to take a look at school accessibility. How accessible are the schools? Okay. So again, we'll apply a 5-kilometer buffer around the schools, and that will look like this. So it's circles, many circles. It's a little cluttered, but we get the idea. And what we'll want to do now is make one area, because if we were to summarize the areas of all these circles, we'd have some double dipping on overlapping areas. So it wouldn't be a representative area. So what we do is a union. So we're unioning all of these different circles so that we get an outline shape, which could be a multi-polygon if they're not all connected. And then we plot this one to see what it gave us. And voila, we have one big shape with a little little second circle. Okay, and then with this, we will calculate the area covered. So for the accessibility percentage, we have to check what is the territory covered by the circles. So we're calculating the area of the accessibility, accessibility area is all the school buffers connected together. And so when we do SC area for that area, we get a single number. Meanwhile, here, when we do it for Vancouver, we get a series of numbers. And the reason why we have this vector is because we have the districts aren't union together. They're all their individual areas. So what you have to do is the sum of this, and then we get a single number. And with that, we're able to find the percentage. Which is...
Before we move on, we have a question in the chat.
Yes.
Regarding the section above. So if you can scroll back to when you created that data frame for the cities. The question was just for the lat and longitude of the major cities. How did you determine the values? Was it like kind of trial and error, or is there like kind of a
these numbers here?
Yeah.
Okay, so maybe I can demo. Am I sharing? Do you see Google?
No, I think it's still on your RStudio.
Okay. I'm just gonna load it. I'm going to share my whole screen.
I think this will be a question relevant to a lot of people who want to maybe do their own data collection and just plot some points in the map. So this will be helpful.
Oh, screen two. Okay, I'm sorry.
No worries.
There's too many windows open. Okay, so all you would do is go on Google Maps. You would select, say I want Pemberton Heights. I click on Pemberton Heights and then I right click and I click here on these dots. Sorry, on these coordinates. And then I can, so I can put them in the right slot. So it's easier with a Tibble because when you paste it, you can actually paste it as is. Your frameworks too. That's it. It's quite simple. It's probably the easiest way to map things for that. We don't know coordinate systems that well. So unless it's coming from an official source, this is the best way to do it.
Yeah, I guess for like an area, you didn't particularly, in this case, like choose like the center point of the location. This data set that you've just kind of made ad hoc was just kind of...
I searched Vancouver and then I did the dot. Oh wow, the sun's quite bright. Okay.
But yeah.
Okay, well, that was how I did it, but that's a good point. You could also make an area, so a boundary, but then again, the easiest point way would just be to select dots and create a polygon out of it. From
like to answer Jeremy's question, like there you can have a very systematic way to like determine the location to put your point in, but it really depends on your use case, I guess, for the data.
Oh yeah.
We just really wanted to be able to figure out roughly where we were looking at on.
Right. Yes. And obviously you look at this and it doesn't look great because why is Coquitlam almost in Port Moody? And so in that sense, it's not centered whatsoever, but because these are electoral districts, all of this is forest. And I don't know why it's so far this way. It's weird, but I'm not going to question the electoral mapping system. So it is what it is. You also have North Van, that's part of Burnaby. Oops. So this is a Deep Cove area, as part of Burnaby. So yeah, these were taken at random from Google Maps, but not the actual centroids of, we could find the centroids and rename it actually. That probably would have been best, but I just wanted us to orient ourselves to figure out where we are on the map.
Thanks.
Yeah, then the next step is, so we booked, okay, so, but this is a good segue into the Voronoi function. And so Voronoi is a technique of, so this would be an example where you want to create, say, catchment zones for the, or analyze the catchment areas for each of the schools. And so that means what territory is covered by this school, for example. And so what you want to do is, you'll combine it. Sorry, Johannes, can you explain what the combine, the difference between, I think, combine and union was?
Combine is just a simpler way of unioning, like making one geometric collection. It's just faster because it doesn't resolve the boundaries. So but for all intents and purposes, it's pretty much the same as ST union.
Yeah, so created a feature here. Then we plot. So we're plotting the Vancouver districts, the Voronoi that we just created, and the Greater Van schools. And so in this case, we're getting the idea that I created a bit of a spider web, but we can't really see what's going on. So again, we'll want to modify to see only the boundary boxes that we created. So in this case, we're taking that school, we're applying ST collection extract, and then doing the intersection with the boundary boxes. So I'm going to call in Johannes again, helpline, ST collection extract.
It's it's self-explanatory. It just extracts the geometric collection out of the object that we have there. And so you can use stcast as well. Stcast without any arguments inside will do the same thing. So usually stcast gets used to convert, say, a series of polygons to a single multi-polygon collection, or a series of points to a multi-point object, or you can do it the other way around. But if you just leave, if you don't feed in any arguments to stcast, it'll do the same thing, and it'll just extract the geometry collection that you're working with.
Okay, great. Thank you. And then we get the Voronoi. So these polygons, as you can see, to understand it, because it's maybe not intuitive, in this case, all the red dots are schools. And so what it's saying is wherever you are in this area, this is the closest school to you. So when you go into the different areas, that's just how this function works. So it's a mathematical equation that does this, and there's probably different methods. In this case is it's looking at area, but there's different techniques as well where you may want to look at densities and treat it differently. And so in this case, as you can see, there's a lot of these areas that have massive territories, but you have to take into account the boundary situation that we're working with, and some places may be waterways, and this is definitely forest, and so it's not perfect. You have to use your judgment when applying these. So do as I say, not as I do. But in this case, it gives you an idea of how to use the function to create territories, areas where you're served by one element in this case. So that's the Voronoi function. And then, so you can use it in urban planning as well to decide. It's a good technique in different contexts. And then finally, this is our last school before the bonus activity. So say you live right next to a school, you don't like it, and you want to see what are the other schools in the area that are close by to this one that may be more appealing. You can create a code as such that allows you to calculate the distance. And so if we look at this table here, it's a matrix. And so as a matrix, I'll create it as a data frame so that you can better see it. Oh boy, got my view. So each of these IDs relate to a specific school. So one is the first school on the list. And so because it's a matrix of distance between each school, you're going to have the one-to-one, two-to-two column or cell that has 0 because it's from 0 meters from itself. And then the distances between them. So this is between school 1 and school 2. And so what you can do here is you could filter and say, if you want to do it manually, you can say, okay, well, 481 is the closest one to school number 1, or you can write a beautiful function that will do it for you. So this is using apply. This is outside the SF realm. ST was the SF part of this. And so with nearest 5, you get you get 5 columns. So the closest, the first closest, second, third, fourth, and fifth. And let's take a look at the final product. So these are the first 5 schools in the list, and we can see their nearest neighbors. Nifty tool. And then finally, the coup de résistance leaflet. So all of this is great. You figured out how to play with the raw SF tools, but then you combine it with, keep doing that, additional tools like leaflet, and you can make works of art. This one is not a work of art, but you could if you had time. So leaflet is quite powerful for visualizations, and especially if you're looking at cities where there's a lot of information that's embedded. I'm sure you could change the background maps and whatnot, and there's all sorts of different functionalities you can do. But this is great in this situation where we're looking at schools because we can see their own version of a Voronoi. And so you can see all the schools. And so you could put information on the tooltips, say like the average grades or all sorts of different information that would be interesting. And so this is the final output, and then you can overlay different SF objects, like in this situation where you have all the different outlines of the district that we added. And you can do, yeah, the world is your oyster. You can do what you want with this. So that's it. I think that's the final. So yeah, we saw quite a few. This was a lot of information, and I only scratched the surface of all the projections and CRS elements. But my goal is to show you what the different functions can do. And I'll take your questions if you have any, and if you want to chat about different activities and things you can do with these types of functions that we spoke about, be very happy to discuss that with you. So, thanks.
So thank you, Véronique. Let me just